Okay, this is the pre-lab lecture video for experiment 9. So in this experiment, we're going to be converting 1-butanol, which is the IUPAC name for this alcohol, into 1-bromobutane using a combination of sodium bromide, which really is the bromide ion, and then sulfuric acid, which will act as a proton source for this reaction. So this is the overall balanced equation. So our goal is to convert 1-butanol to 1-bromobutane, and this mechanism is nucleophilic substitution that's bimolecular. Now, some of you will have already gotten to this by that week, the people that are in my class. I don't know if the people that are in Dr. Kwan's sections will have gotten quite to SN2. So what I'm going to do is I'm going to give you an overview of the mechanism of SN2 reactions and also of some of the side reactions that are occurring in this experiment. And I'll also make a link to the full-blown lecture videos from my classes. If you don't want to watch those, you can look in your textbook, the SN2 reactions, as well as the conversion of an alcohol to a double bond, which turns out to be one of the side products. Those are covered in sections 6.8 and 7.10 of the Wade textbook, either the 8th or 7th editions. So what we're going to do is we're going to be running the reaction by performing reflux. We're going to isolate the product by steam distillation and extraction, and then we'll perform a simple distillation to purify the 1-bromobutane product. And we're going to analyze its product using two methods. One, a method that you'll get into much more detail next semester called infrared spectroscopy, and then gas chromatography that we did with the cloves experiment. So when we have nucleophilic substitution, what that means is typically nucleophilic substitution is done with a halogen. So if we take a halogen like a bromine, chlorine, or iodine, and we react it with a negatively charged nucleophile, and the negatively charged nucleophile has a lone pair, that's what makes it a nucleophile, that's what makes it electron rich, and also what gives it its negative charge. What we end up doing is reacting that negatively charged nucleophile with an alkyl halide. We end up forming the carbon nucleophile bond, and then in the substitution forming a Br minus or Cl minus, whatever this halogen started out to be. So this is called nucleophilic substitution because I'm substituting one nucleophile and generating another one as a product. So in this experiment, what we will be doing is we will be taking an OH group, and in essence, we're going to be substituting that OH group for a Br. Now, the mechanism's a little bit more difficult than this, but we're going to be substituting the OH group for the bromine, so it is a nucleophilic substitution reaction. Only it'll require another additional reagent in order to have the OH group be substituted for. Now, typically what happens is that in a nucleophilic substitution reaction, and I'm just going to make one up here and use hydroxide ion, and I'm going to react that hydroxide ion with just a generic organohalogen or alkyl halide. So X could be chlorine, bromine, or iodine. Could be fluorine as well. What happens in this reaction is, in the substitution reaction that we're going to do, the nucleophile will come in and donate its pair of electrons to this carbon of the alkyl halide. Now, that alkyl halide, the reason that it is reacting that way is because the carbon of the alkyl halide is slightly positive. The halogen is slightly negative, which is what made this carbon slightly positive. So in this case, my nucleophile is my electron-rich species. and that's the hydroxide ion. And then the carbon has a delta positive charge on it, so it's going to be my electron poor species, which in essence is going to be what I call my electrophile. So back in the Lewis acids base sections of the textbook that we talked about what seems like forever ago, a few months, electron-rich species or the Lewis bases are defined as nucleophiles, and the electron poor, or what are called Lewis acids, are defined as electrophiles. So what happens is that the hydroxide comes in and it attacks this carbon, or it donates its pair of electrons to form a carbon-oxygen bond. But it can't do that unless one of these other carbon bonds breaks, because we can't have 5 bonds to a carbon. So at the same time the hydroxide is forming a CO bond, the carbon-halogen bond is breaking, so that this reaction will occur with one step, and that's what we call a concerted reaction. And we'll end up then replacing the halogen with the hydroxide group. And so that's our nucleophilic substitution. Now it turns out that for the reaction that we're going to do, since this is a one-step concerted reaction, this is the SN2 mechanism. The actual molecule that we're going to use here has a primary carbon attached to the halogen in this case, and it forms still a primary carbon when we're all said and done. And the only types of substitutions that can occur at a primary carbon are SN2 or SN2, which is called bimolecular nucleophilic substitution. So we have our hydroxide coming in, attacking the carbon, and kicking off the halogen group. And this actually has to occur by this geometry. This is what's called backside displacement. So that the so that the nucleophile comes in and attacks this carbon down the carbon-halogen bond. So it attacks it from the backside, and then the halogen leaves. Now the transition state for this reaction would have formation of a partial oxygen-carbon bond at the same time the carbon-halogen bond is breaking. And they have to be in a linear geometry because of the backside displacement. Then your 3 atoms or 3 groups that are attached to this carbon would then adopt a trigonal planar geometry, so that what we have is what's called a trigonal bipyramidal transition state. So as the hydroxide comes in and attacks this carbon, these 3 groups fold up to become planar, and we have these partial bonds between the oxygen and the halogen. Now, if you're thinking that I wrote a carbon with 5 bonds, I didn't. I wrote a carbon with 4 bonds because the CO and the CX bond are each worth like half. Now, in this process, the oxygen is going from being -1 formal charge to being 0 formal charge. So in this process, the oxygen is slightly negative. The halogen is on its way from being having a 0 formal charge to -1, and so it's delta minus. So what's happening is that the negative charge on the hydroxide is being transferred through to the X minus, and so this would be the transition state of this one-step SN2 mechanism. Now I'll get to exactly what goes on in the reaction that we're going to do today, but it will be a concerted one-step mechanism after we do something. Now the halogen here is being kicked out, and so that's actually what is called a leaving group. And so the leaving group leaves either on its own, or it gets kicked out as the nucleophile attacks or forms the bond to that carbon. And that leaving group is going to become important in a few minutes. So here's just a generic SN2 reaction. of a negatively charged nucleophile replacing a halogen in an alkyl halide. Now, that substitution, we are also going to look at elimination reactions that occur in this experiment as well as side products. There's also another nucleophilic substitution that occurs. But what happens in elimination is that if I have my carbon that's attached to my halogen, then I call the carbon that's attached to the halogen or the carbon that's attached to the leaving group, the terminology here is that I call that an alpha carbon. And then the carbons that are attached to that alpha carbon are called beta carbons. There's nothing spectacular about that. And the hydrogens that are attached to the beta carbon are called beta hydrogens. And so the other possible reaction of an alkyl halide that can occur is that at higher temperatures, and I'm just going to deal with what we are looking at in this experiment, when we're doing a 45-minute reflux on our alcohol, what could happen is that we have a carbon that's attached to the leaving group. One of these beta hydrogens could actually, we could break the carbon hydrogen bond, have this beta hydrogen leave as an H+, have this pair of electrons move here to form a carbon-carbon double bond between the alpha and the beta carbons, and then at the same time have this carbon halogen bond break and lose that halogen as an X-. So in this elimination reaction, we would basically form a carbon-carbon double bond. We would have our H+, and then we would have our X- formed as a result of this reaction. And this can occur at high temperatures, which is what we're going to be doing by refluxing our solution for 45 minutes. So we can either get substitution or elimination, and these are the basic mechanisms for this. Would be called E2. This is actually, well, I don't know that it's E2, but this is a generic form of elimination that would occur for an alkyl halide at high temperatures. You might say, well, is there anything pulling off this hydrogen? And the answer is, you could probably say that that water is basically collecting the hydrogen after it becomes H+ to form the hydronium ion. But the water's not actually taking an active role in pulling the hydrogen off. The thermal energy in the reflux will cause this H+ to be lost. The most important reaction is the SN2 reaction, but we will see have the possibility of forming some elimination product along the way, although we won't see it in our final product, and I'll explain why later. So bimolecular nucleophilic substitution then is, as I said, we take a nucleophile, it comes in and attacks, in this case I'm going to say a primary carbon, so I'm just going to put an R group here. I have generically a leaving group, so that leaving group could be a halogen, and so the nucleophile comes in, donates its pair of electrons to that carbon. At the same time, the carbon leaving group bond breaks, and the leaving group then gets that pair of electrons in the bond. We go through a trigonal bipyramidal transition state where the nucleophile is partially bonded to the carbon, which is partially bonded to the leaving group. The three atoms, in this case the hydrogens and the R group, then become trigonal planar. We get this trigonal bipyramidal transition state where the nucleophile is slightly negative in the transition state, and the leaving group is also slightly negative in the transition state. And hopefully everybody's talked about transition states, but all the transition state is the high energy species between the reactants and the products. And these dotted lines indicate where the bonds are being formed or broken. In this case, in this one-step concerted mechanism, we're both forming and breaking bonds at the same time. and then the charge is being transferred, the negative charge from the nucleophile to the leaving group. And then that gives us a final substitution product where now the nucleophile is attached to the carbon, and then we've lost our leaving group in its anion form. So this again occurs by backside attack, but this is the overall mechanism. There is one small problem with the alcohol that we're using, and that is that in order for the leaving group to leave, what we need is what we would call a good leaving group. And it turns out that leaving group ability is based on basicity. So in the experiment that we're actually going to do, we're going to take sodium bromide. Okay, and the sodium is just going to be a counterion. But we're going to try and take this bromide and react it with our 1-butanol. So now we've got a CH2, CH2, CH3, and I'm actually writing now the structure of the butanol. The problem with this reaction as it stands now is, since this is a primary carbon where the substitution is going to occur, it has to go by the SN2 mechanism. You have no choice when you're a primary carbon. You have to undergo substitution by the bimolecular pathway. But the problem here is that the leaving group, this OH group turns out to be a strong base, at least as far as it's a stronger base, and so therefore it's actually a very poor leaving group. Leaving group ability is based on one thing, which is basicity, and it's inversely related. So whereas halogens are weak or even non-bases, they don't react with water, the halogens are poor bases, and so that makes them great leaving groups. The problem with the hydroxide is a fairly strong base, and so that means it's a lousy leaving group, and it actually won't leave until I do something to convert it into a better leaving group. And so what I'm going to do is, first I'm going to erase my writing here so I can clean this up a little bit and make it a little bit more straightforward. Hopefully you wrote that down. If hydroxide won't leave on its own, instead what I'm going to do is I'm going to force it to leave by converting it to a weaker base. And so H2SO4 will give up a proton to the water solution, and so what will happen is we will protonate this alcohol first. The acid will actually react with the OH to form what's called an oxonium ion. So this is a simple Lewis acid base reaction or electrophile nucleophile reaction. I'm going to protonate this oxygen. So a pair of electrons on the oxygen is going to be used to protonate or used to form an OH bond. And so I'm going to turn my alcohol into a protonated alcohol. And so the oxygen now is going to have, it owns a grand total of 5 electrons. It started with 6, so it has a +1 formal charge. And so the H plus protonates the alcohol, and the arrows have to move in this direction from electron rich to electron poor, or the arrows have to move towards the positive charge. You want to make sure your arrows always go in that direction. But now what I just did was I just converted an OH group, which is a pretty strong base, to when this molecule leaves, this will leave as H2O, and H2O is a much, much weaker base than hydroxide is. So by protonating the OH group, I've converted a strong base into a weak base. And so now the bromide will be able to come in Of course, it's going to take a little bit of heat to do this reaction, 45 minutes worth of refluxing heat. But now the bromide will be able to come in, attack this carbon, and then kick off the oxonium ion, and that's what this is called. I will write that down. This is called an oxonium ion. So it'll kick off the oxonium ion as a water molecule. So that means that we'll go through our transition state, where we have the bromine partially bonded to the carbon, which is then partially bonded to what's going to become a water molecule. We will have had our groups, our propyl hydrogen groups now become planar for our transition state. And so the bromine now we have to, if we're going to write the transition state here, we have to be careful because now we have to put our charges in. We do have two partial bonds, one forming between carbon and bromine and one breaking between oxygen and carbon. Now our bromine is going from, and let's just write the final product here so it's easier to see what we're doing. I'm going to end up forming the bromine carbon bond, and now I'm going to end up with my CH2, then my CH2, CH2, CH3, so I'm going to end up with one bromo butane and my water molecule, which now was the leaving group. So if you look at the charges here, bromine is going from -1 in the reactant to 0 formal charge in the product. So bromine at the transition state is slightly negative. That negative charge is being transferred from the bromine to the oxygen. The oxygen started out with a positive charge and is now going to being a formal charge of 0. So in the transition state, the oxygen is slightly positive. So the negative charge is going from the bromine to the oxygen, and then these would be my final products. So the reason we're using H2SO4 is that H2SO4 will give up a proton when it protonates the OH group. And the OH group then becomes a good leaving group, and the bromine then will be able to kick off the oxonium ion, or the water, and then we'll be able to make our final product. Now, H2SO4, when it loses an H+, it becomes HSO4 minus. Remember our sodium over here that was the counter ion to the bromide. The sodium then becomes the counter ion to the HSO4, and so that gives us then our overall balanced equation. The acid in this case is a reactant. It is reacting, and so we do need to treat it as if it was potentially a limiting reagent. Okay, so in your pre-lab assignment, when you're asked to calculate the limiting reagent, you do have to include sulfuric acid as a potential limiting reagent. It probably won't be, it'll probably be in excess, but you still need to calculate how many moles of H+ you have in that molecule. All right, so this is basically our SN2 mechanism with our transition state. So we've converted the OH to a good leaving group, and then with a lot of heat, we can cause the substitution reaction occur to form our final products. Along the way, though, there's some side products that may occur as part of this reaction. And so I think the next slide is for side products. So along the way, a couple things can happen. The first thing that can happen is that we are heating this solution to a fairly high temperature in order to reflux it. And so we could end up, after we form our oxonium ion from the 1-butanol, we could end up with a side product of elimination. So this could eliminate in the heat to produce a double bond. So the mechanism that I showed you before, this H would leave as you take this pair of electrons, move it here. Now this oxonium ion again is a decent leaving group, so we break the carbon-oxygen bond, and so we would have the H+ and then we would have our H2O. The leaving group leaves as H2O. So one of the possible products is the elimination product that would form this molecule and H2O and then acid. And so this is called 1-butene, is its IUPAC name. So we could have elimination of this alcohol, this protonated alcohol, in the heat. Now this would be a one-step process. There would be a transition state for this reaction. So if I was writing the transition state, I would actually have to show all the bonds that are being broken, and in this case, the bond that's being made. So if we look at this, the carbon-hydrogen bond here is breaking, so that gets a dotted line showing that the carbon-hydrogen bond is partially breaking. I am forming a carbon-carbon double bond here, so I need to show that as a dotted line. And then the carbon-oxygen bond is also breaking, so it gets a dotted line. So I'm breaking the CH bond, forming the double bond, and kicking off the leaving group in this transition state. Now as far as charges go, the hydrogen here, and remember this, okay, this is my alpha carbon, this is my beta carbon, so this is my beta hydrogen. That's why I chose that one, because that's the beta hydrogen. The beta hydrogen here is on its way from being 0 formal charge to having a +1 formal charge, therefore it's delta plus. The oxygen is on its way from +1 formal charge to 0 formal charge, so it's also delta plus. So what's happening in this case is the electron movement will leave the H as an H plus as a proton, and then this oxygen will pick up that extra electron or extra electron pair, because water will then be formed with a lone pair. Okay, so this would be our transition state for that elimination side product. Now there's also one other side product that is somewhat unlikely to occur, but we still need to deal with it. And that is that it's possible for two alcohols to react together in the heat to form an ether. So if you think about it this way, remember how I wrote my oxonium ion, so I'm just starting here with the oxonium ion, and then I have my H, my other H, and then down here I have my propyl group. It's also possible that after you've protonated the alcohol of one of the butanol molecules, that this alcohol, another butanol molecule could come in and do bimolecular substitution. And so you could have the formation then of see, that would be a dotted line. It's also possible that you could have the OH group of the alcohol come in and attack this carbon and then kick off the water as the leaving group. Now, for those of you, particularly in my class, who said, wait, this is a neutral nucleophile, it's a pretty weak nucleophile, and weak nucleophiles normally don't undergo SN1 or SN2 reactions. You're right, neutral nucleophiles don't normally undergo SN2 reactions, but remember, we're refluxing this reaction for a fairly long time, so it is possible for this to occur. Now, if it was to occur, what you would have is you would have this carbon then, this oxygen, would be forming a partial bond to this carbon would be forming a partial bond to this oxygen. Let me just write in my charges here, and I'll show you where this positive charge over here comes from. You already know that this OH group, or this H2O group, when it leaves, that oxygen will go from +1 to 0 formal charge. So that's why this oxygen has a delta plus charge. Okay, so there's my transition state. So now I'm going to go back and then write what the final product would look like, or what the initial product would look like. So once the water leaves, I'd have the oxygen attached to a hydrogen with a lone pair, then attached to the carbon with the hydrogen, the two hydrogens, and the other propyl group. So I would end up with this as my product, and then over here the H2O after it has left. Now this oxygen over here has 4 sets of electrons, but it only owns 1, 2, 3, 4, 5. So it would have a positive formal charge. And so then this oxonium ion would lose a proton. So what would happen along the way is you would break this oxygen-hydrogen bond. That would come down there. There would be a transition state for that. It would be the oxygen-hydrogen bond is partially breaking. And that oxygen is going to go from, once this OH bond breaks and the pair of electrons goes back to the oxygen, the H then is going to leave as an H+. So I'll leave the transition state here and then I'll come back to it, because the final product's going to be CH3, CH2, CH2, CH2 with the O then attached to this on this side, which is a CH2, with then my propyl group. So the final product plus then the H+. So this is actually called dibutyl ether. And so this proton then, once I break this oxygen-hydrogen bond, that will leave as an H+. So that'll come down here. And the transition state then shows the breaking of the OH bond. The oxygen is going from +1 formal charge to 0. So it gets a delta plus. And this hydrogen here is on its way from being 0 formal charge to +1 formal charge. Therefore, it gets a delta plus as well. And so that would be the final transition state of the side products. So as a part of the high temperature environment of this reaction, we can get a number of side products, two major ones. The formation of the 1-butene by elimination of the beta hydrogen and the oxonium ion. And the other side product is the reaction of the other side product is the reaction of 1-butanol with the protonated butanol and with the oxonium as its leaving group going through, and this would be an SN2 mechanism. It would then have the oxygen partially bonded to the carbon, partially bonded to the leaving group in the transition state, and would then give us our final product of dibutyl ether. So in the pre-lab assignment, I've asked you to sketch out the mechanisms for the formation of these side products. I just did that for you. And some of you will have done this in lecture and others will do this shortly. Okay, so those are the two major side products of the reaction, the formation of the 1-butene and of the dibutyl ether. Okay, so ideally then, we're going to get the SN2 reaction of where the bromide is going to come in and replace the oxonium ion to give us our 1-butyl bromide. So let's just go over the experimental procedure kind of quickly. We're going to do reflux, which basically just means boiling with condensation. So we're going to set this apparatus up with our Bunsen burner, our wire gauze and O-ring. We're going to have our mixture of, in this flask will be our mixture of our H2SO4, our sodium bromide, and our 1-butanol. And once we have that mixture, we're going to add boiling stones to it, and it's critical you add boiling stones because if you don't, you're going to end up with a fire. So the sulfuric acid, this mixture then is heated to boiling. What will happen is the vapors will come up into the condenser, and hopefully we want the vapors to go no further than halfway up the condenser. So we don't want the vapors to go any higher than that, because if these vapors come out the top, they'll come right down onto the flame and we'll have a fire that way. So we want to control the heat so that the vapors only go up about halfway into the condenser. Now this is called reflux because what will happen is the solution will come up, condense, and then keep dripping down. And so this way what we're doing is we're boiling the solution without losing any product. Because what's going to happen is we're going to start with butanol that has an OH group, so it has fairly strong intermolecular forces, and we're going to convert that product into an alkyl halide that has weaker intermolecular forces. So if we didn't have the condenser here, we would just basically boil away all the butyl bromide after it's been formed. So in the reflux is to keep the butyl bromide back in solution. And what you'll actually see during this experiment is there's many different colors that this will turn. Some people's will be purple, some people's will be red, some people's will be brown. Very rarely is there no color. But you'll get a second layer formed in the round bottom, and that second layer then turns out to be our alkyl halide product. So as the reaction occurs and the alcohol is being converted to bromide, bromide's not water soluble. So you get a second layer that floats on top, and that's actually how we know that the reaction has occurred. Now, safety issues with this: after you get your apparatus set up, you're going to have a TA, an instructor, and look at this. And so the instructors are going to look at the following. We're going to make sure that there is here, that there's no air gap there. Because if there's an air gap, those vapors will literally catch on fire from the Bunsen burner. And then the other thing we have to do is to just make sure that your vapors don't go halfway up the condenser. Okay, so you're going to set this apparatus up. You're going to reflux this for 45 minutes. That's how long it takes for the reaction to go to completion. After the 45-minute reflux period, and you're keeping track of this the entire time, you're noting your colors before the reflux, during the reflux, and after the reflux. Then we go to, after the 45 minutes of reflux, you're going to shut the Bunsen burner off. You're going to let the apparatus cool. You're going to basically then move the condenser over here, put a distillation adapter, thermometer, and thermometer head, your vacuum adapter. And so what you're going to do is you're going to basically convert the reflux apparatus into a simple distillation apparatus. You don't have to clean anything. You're just going to use the condenser as is. So then what you're going to do is then you're going to distill this solution, and this would be technically called a steam distillation. But you're going to distill this until that top layer ends up into, and we're going to do this into an Erlenmeyer flask, not the beaker. So you're going to distill this until the top layer is completely gone, or the temperature will start to rise because now you're distilling acid, so it'll go up to about 115 degrees. This usually has a red, orange, some other color, so it's easy to see when it's gone. So you're going to slowly distill or quickly distill this until that top layer is gone. And then over here now, we will have a myriad of products. The possible products that we collect after distillation are water, sulfuric acid, of course, our hopefully 1-bromobutane product. We could end up with some unreacted alcohol. We could end up with our 1-butene side product, and we could also end up with our dibutyl ether also as a side product. So all of these materials then, all of these components could be in my reaction mixture. And so we have to go about then separating each one of these components using a series of extractions and then a final simple distillation to get rid of or to purify our final alkyl halide product. So the way that it looks here as a second layer, and the way that it even looks after the simple distillation, hopefully at the end you'll have a nice clear colorless liquid. Okay, but these products right here are important because this is where your separation scheme starts, is separating these 6 products away from each other. So we're going to do 3 extractions. And each time you do an extraction, you're going to have to find out which is the aqueous and which is the organic layer. Although to be honest with you, the smallest layer is probably your alkyl halide. I will caution you, you do not throw any layer away until the final product has been collected. So the first thing we're going to do is we're going to do an extraction with water. What's the water going to do? Well, the water, in terms of the extraction, is going to, we're going to get 2 layers here. We're going to get an aqueous layer and an organic layer. I don't know which is which because it changes between students. What's going to be in our aqueous layer? Well, water, duh. Then what else are we going to have? We're going to have sulfuric acid if we had a few traces of that to still over. And of these products, that's about it. The alcohol isn't water soluble, the alkyl halide's not water soluble, the dibutyl ether's not soluble, and the alkene is not water soluble. So after our first water extraction, we're going to basically be removing any sulfuric acid that's left from the distillation. But then you're going to say, but then we add more sulfuric acid. So if we add more sulfuric acid here, we're going to end up with, again, 2 layers. Now, why am I adding sulfuric acid in this second extraction? Well, let's go back and look at our products. What happens if I add H plus to my dibutyl ether? If there's dibutyl ether present, it's going to become protonated. Once it becomes protonated, it becomes ionic. What layer does it go into? Aqueous layer, or the sulfuric acid layer. So sulfuric acid layer could remove, or will remove, any dibutyl ether that's present. What else could the sulfuric acid remove? How about any alcohol that's present? Because if you have any unreacted butanol, it will also react with sulfuric acid, and now you'll make an oxonium ion here, and that also is ionic, and that also will dissolve in the sulfuric acid layer. So the idea here of the sulfuric acid layer is the sulfuric acid layer will then remove our dibutyl ether and any unreacted 1-butanol. Okay, so we're taking advantage of that acid-base reaction between the alcohol and the acid to remove those. One is an unwanted side product, and the other one is actually an alcohol, is the starting material. Okay. Now, what is the 3 molar? So we separate those two layers. What's the 3 molar sodium hydroxide there for? Well, after you separate those layers, you're going to have, hopefully, butyl bromide. You may still have some of this product formed, and in a few weeks, you would see that that went away with the sulfuric acid, but I'm not going to discuss that now. So we'd have that product. We would also have a trace of H2O, and of course we'd have a trace of sulfuric acid. So what does the sodium hydroxide do? It neutralizes the sulfuric acid that's present, and so then if there is any sulfuric acid present because it's difficult to cut the layers exactly, the 3 molar sodium hydroxide will then basically neutralize any acid that's present. So when you're done with the 3 molar sodium hydroxide extraction, and again you'll have to find out which layer's which, you should end up with a layer containing the bromide, the alkene, and then trace H2O / sodium hydroxide. Okay, so you need to determine the aqueous and organic layers, and you need to keep these in separate containers until the end of the experiment, because people will get these layers completely messed up. But we'll deal with that during the experiment. We're then going to dry the alkyl halide with calcium chloride pellets. Calcium chloride will remove the trace amount of water and sodium hydroxide. It does have an advantage in the fact that it does have pores. And so if any butanol made it through this process, the butanol will stick in those pores, and so we will remove it. But it's unlikely that the alcohol made it all the way through, simply because it was probably removed by the sulfuric acid. So then, after drying the solution, and for calcium chloride pellets, they're pellets, and so they don't clump or not clump. So what you're going to do is add the appropriate amount that it says from the procedure, and then after you swirl the calcium chloride pellets, if your solution is clear, then you know you've added enough. If the solution is not clear, then you need to add a small amount more. So drying with calcium chloride is a little different than drying with sodium sulfate. So calcium chloride, we know you've added enough calcium chloride when the solution is clear. Okay, might make a good quiz question. So then after we've got our solution, which should at this point just contain the butyl bromide and maybe a touch of alkene, we're going to go ahead and do the final purification using simple distillation. Now, one of the things that we should note here is the alkene is nothing but a hydrocarbon. It's a C4H8 hydrocarbon. It boils probably in the neighborhood of about 35 degrees. So if it made it through with all of the heating and everything else, if it didn't evaporate to get to the final product, when we do our distillation, it's going to basically become a vapor, but it's never going to condense. So in the final distillation, if there's any there, it's going to be gone by that time. So what you're then going to do is you're going to rinse out your simple distillation apparatus that you used. You're going to have to dump out the sulfuric acid solution that remains in the round bottom. You're going to pour that down the drain with copious amounts of water. You're then going to want to dry that with acetone. You're going to want to rinse all of the pieces of the simple distillation apparatus with acetone. And then you're going to set up the simple distillation again. And in this case, add a couple of boiling stones. And you're going to go ahead and you're going to quickly distill the product using the Bunsen burner and the wire gauze. You're going to quickly distill the solution, recording the boiling point, and you're going to collect it into a tiered sample vial. And at this point, your solution should be colorless and clear. It should be nicely purified butyl bromide. And we'll get sample vials so that you can only have to collect into one of those, but you might have a substantial amount of butyl bromide. Okay, the problem here is going to be we're using a Bunsen burner, so we do not want to distill to dryness because the flask could crack. So once you've distilled 3/4 of the alkyl halide by eye, shut the Bunsen burner off and the remaining 1/4 will distill, and then we won't have a flame on the round bottom when it's dry, and so it will have no possibility in cracking. Okay, so at the end you're going to have your product in your tiered sample vial. Then we're going to analyze the purity of the product. After you're going to determine your mass, of course, and calculate your percent yield based on the theoretical yield that you calculated in the pre-lab assignment. We're going to take some of that butyl bromide, we're going to inject it into the gas chromatogram, and we're going to get a GC trace to show you how pure your product is. Now, in terms of the GC trace, I won't know exactly what the retention times are until I actually set the instruments up. But generally, the alkyl halide has a lower boiling point than the alcohol does. And so we should see just the alkyl bromide or the butyl bromide peak, and we shouldn't see any alcohol in our product. We also shouldn't see any water or any indication of moisture. And where the alcohol will show up, I won't know until the instrument is set up and running, and then we'll inject some pure alcohol to note where its retention time is, so that there'll be a sample chromatogram will be on the Blackboard site probably after the first couple of chromatograms have been run. So that's our first test of purity. It's actually our second test because the first test of the purity is the fact that how clear and colorless is it. If it's not perfectly clear and perfectly colorless, then there is some indication of impurities. The second test will be what's called infrared spectroscopy. Now, infrared spectroscopy is a technique that you'll talk about in detail next semester as part of the Organic 2 lab. But infrared spectroscopy basically allows us to analyze products, and what it does is that when you have, for instance, a carbon attached to an oxygen, attached to a hydrogen and an alcohol, this OH bond actually vibrates back and forth at a particular frequency, and that frequency turns out to be the same frequency as a particular wave, as a particular type of infrared light has. So this OH group actually vibrates back and forth at an infrared frequency. That's why water acts as a greenhouse gas and traps and absorbs the infrared light that comes in from the sun. That's why CO2, if you had a CO2 molecule, the CO2 vibrations are the vibration of these two atoms back and forth in the bond, what we sometimes call bond stretching. That vibration also occurs in the infrared region. That's why CO2 is a very powerful greenhouse gas, and that's why it absorbs a lot of infrared. But the key thing we're going to do is we're going to look for any presence of this OH stretch, which occurs in this part of the spectrum, which is approximately 34 to 3500 what are called wave numbers. And again, you'll talk about that in detail next semester. So if this peak is present, you have OH in your molecule, whether it's water or whether it's alcohol. What we'd like to see is we'd like to see no stretch, and we'd like to see this peak just go like there and then this peak to be gone. So this isn't a quantitative test, it's more of a qualitative test to show that we've taken the alcohol and gotten rid of the OH group and formed the alkyl halide. And so that'll be a second qualitative test of your purity. Your two qualitative tests will be appearance and IR, and your quantitative test will be of the 1-bromobutane. We're not going to determine the refractive index because the refractive index of the alcohol and the alkyl bromide are very similar, and we can't get any quantitative information from that. So the three tests of purity are appearance, IR, and GC. Okay. Now, when you're all said and done, you're going to determine your mass of your bromobutane product, calculate the percent yield. You're also going to, after you got the GC results, you're going to prepare a table of GC results. You're going to include your IR spectrum. You're going to label whether the OH peak was there or not, and then you're going to use that to prepare your discussion of purity of the final product. At the end of the experiment, you're going to wash all the glassware carefully because there's some concentrated sulfuric acid in it. So you're going to wash the glassware very carefully, and you're going to rinse any remaining acid-base solutions down the drain with copious amounts of water. A full written report is due for this experiment, and the contents are in the experimental handout. In other words, which sections of the lab report you are going to be turning in, which pretty much will be almost everything because you do have side products and you do also have a mechanism for this reaction and everything else. So this will be a full-blown lab report, and the details of that as well as the details of what to do in the handout, and you will want to use the grading rubric for the lab reports to make sure that you've included all the sections. Okay, so that's what we're going to do in experiment 9. You want to make sure you do your pre-lab early, because you will have to write some mechanisms, you will have to outline the procedure, and for you to do the mechanisms, I just wrote them all for you, so you just got to sort out where they are in this video, but don't wait till the last minute. Of course, if you're hearing this at 2 o'clock in the morning before your lab period, well, you waited till the last minute.